of these random variables, x, z, and u, what word in that problem statement is key here? Independent, exactly. So because of that, we know that the PDFs are, or that the joint PDF of them is the product of the individual PDFs. Now, the second key insight here is, well, we have, let me now start to write, actually I can just write the solution here. And so we are saying the expectation of e to the power of x plus z times u is, of course, the expectation of e to the power of x plus z times u conditioned on a particular value, small u of u, then multiplied with the PDF of u. That is the law of total probability that we discussed at great extent last time. And so this is usually something that you can use in a lot of situations. When you have a complicated combination of variables, then it's often useful to say, well, let's condition on one of them, solve the problem for the others, and then that is going to give us the total solution. Sorry, f of u du. And you might wonder, well, why am I conditioning on u? We're still stuck with two random variables up here. Right? But you see that x and z have the same type of distribution, and they're independent of each other. So therefore, the results for the sum of them is going to be relatively easy to compute. So that's why we leave it standing like this. And then so because u is a uniform distribution, this is just becoming minus 1/2 to 1/2 of the expectation of e to the power of x plus z times u du. Now, because x and z are independent, this is actually 1/2 expectation of e to the power of x times u times the expectation of e to the power of z times u. And so you see the very strong similarity of this problem to what we said for moment generating functions, that the sum of two random variables, their moment generating function, is the product of the MGFs of the individual contributions. And here we have essentially the same thing, right? The expectation of e to the power of x, that's just an MGF formulation. So therefore, this is becoming du. And then we know that the x and the z are exponentially distributed random variables, so but we know what is the moment generating function of a random variable, or you can just say, well, we know the distribution, so therefore we can easily solve that integral of the expectation. And either one works, and so this becomes minus 1/2 to 1/2 of 1 over 1 minus u. That's the MGF, or that is the expectation of e to the power of x times u. And because we have the product of that, it's of course squared du. Now that, as we all know, is 1 over 1 minus u, evaluated between minus 1/2 and 1/2, which is 1 minus 1/2 minus 1 over 1 plus 1/2, which is 2 minus 2/3, which equals 4/3. Okay, and that was the solution to this problem. So the math in this whole thing is really fairly straightforward, but again, the key insights here is we have independent variables involved in here, which makes treating the sum of the two random variables, in particular the e to the power of the sum of two random variables, as fairly straightforward. And the extra complication of the of the multiplication with u is being handled by first conditioning on a particular u, and which allows us to solve the problem for the x and z, and then integrating over this expression multiplied with the PDF of u. Okay. One more thing in the preparation for the midterms, you will see today we're going to go through through random vectors, and we're just going to have a whole rat's tail of rather complex equations. So in order to make sure that the midterms is not just an exercise in memorization, what I'm going to do is I'm going to put together a bunch of equations that will be made available as an extra sheet on the at the exam. So in other words, you cannot write up your own cheat sheet, but I am going to give you a summary of the most complicated equations as a cheat sheet that you are going to have at the exam. And then I'm going to try and get this done by this weekend so that you know which equations you need to memorize and which you don't. And I will consciously not include some of the equations in there. I might actually go so far and write down more equations, but for some of them indicate they will not be on the cheat sheet, but give you pointers of how you can remember them. And so, for example, for the LM distribution, there is really no need to memorize the moment-generating function, because if you know the MGF of an exponentially distributed variable, you just need to understand how MGFs of products of of sums of random variables work, and know that an LM is the sum of multiple exponentially distributed variables. So these are insights that you should have, and that's the explicit reason why I'm not going to include the equation, because you should be able to have that insight to understand how you derive it. Right? But there are other equations where it is relatively pointless for you to just memorize them, and they get pretty complicated. So those will be available on that cheat sheet, and hopefully that's going to help you to maybe focus your preparation more again on understanding the principles and applying them, and not spend all of your mental energy on memorization. Okay, so far to the administrative things. Now let's return to the scientific material. So last time we finished with an equation for the sum of random variables when the number of terms itself is random. And we were saying that this is actually the moment generating function of n, of the number of terms, evaluated at the logarithm of the moment generating function of the individual terms, called phi x of s. And then we said this is the moment generating function of our, what did we call it, I think, w. Now, remember there were certain conditions attached to it. Conditions were that the individual terms of the sum are independent, identically distributed, and that the number of the terms is independent of the individual summand terms. But if that is fulfilled, then we have then this equation can be applied. And we didn't really have the time to go through an example last time, so let me catch up with that. So we have a number of packets, of data packets that we're transmitting, and that is a geometric probability mass function with an expectation of n, which is of course 1 over q as per definition, of 4. So let's just say number of packets per second that is being transmitted. And then we have a number of bits per second, sorry, of bits per packet, which is a geometric distribution with expectation being 1 over p being 10 to the power 3. So now we want to find out what is the PDF of number of bits. And so we see that the conditions are fulfilled that we set for this sum here, and therefore we can now say, well, first of all, what is the the probability generating function of n? Well, it's q times e to the power of s divided by 1 minus q times e to the power of s. And similarly, our phi for the number of bits, let's call it k. Sorry, this should be expected value of k. And is p times e to the power of s divided by 1 minus p times e to the power of s. So if you're wondering about this equation, we went through that several lectures ago, so this is one of the equations that you might find on the cheat sheet, or otherwise you probably will want to memorize that, but it's also not that difficult to reproduce, and because you just need to go into the defining equation for the moment generating function, plug in the PMF of an exponential, and that's just a very straightforward integral. And so since we are evaluating at the logarithm of phi k of s, we can say that the e to the power of s that we have here in this expression phi n has to be now replaced with a phi k of s. And so remember, we're saying we're evaluating phi n at an argument of ln of phi k of s. So normally, wherever we are finding s in the equation for phi n, we have to replace that with the ln of phi k of s. Now, since the s here always shows up as e to the power of s, that means the e to the power of s has to be replaced by the phi k of s. So therefore, we can now write phi n of s as q times. Now replace this term here with this bunch of stuff. So this is p times e to the power of s divided by 1 minus p times e to the power of s divided by 1 minus q. And again, this e to the power of s term gets replaced by this thing here. And so we're getting p times e to the power of s divided by 1 minus p times e to the power of s. And now that, of course, needs to be simplified further, which is the main reason why we're saying what is the PDF. And so let's first of all rewrite this as p times q times e to the power of s divided by 1 minus p times q times e to the power of s. And now we have to do the back transformation from the Laplace domain, from the S domain, into the original domain. And as we know, inverse Laplace transformation is not exactly easy. However, the way that we usually have it applied is to just say, well, can we recognize the form of this moment-generating function? And so we're just going in a sort of reverse tabulation, because we are not doing Cauchy residuum integration or anything, contour integration here. And if you look at this, it's actually, again, a geometric random variable. And that's exactly the form that we have for all of the other expressions here as well. And it's a constant times e to the power of s divided by 1 minus that constant e to the power of s. Same shape here. So in other words, what we observe here is that this is simply geometric with a mean of 1 over pq. So this is 4 times 10 to the power of 3. So this is a slightly unusual result, right, that we're saying that, well, we have a random sum. The number of sums, the number of terms is a random variable. The contributions is a random variable, and it ends up being that same shape for the PDF. That's just because we have a geometric PDF in this particular case, and things work out that way. That's not a universal law, obviously, right? But it's just a result for this particular problem statement. Now, we can, however, derive some universal laws. Well, it's actually still random sum of IID, and n independent of summands. We say that the expected value of W is the expected value of n times the expected value of x. And so that is very much in agreement with the result that we just saw. Right? But the result that we just got is stronger because it gave us the whole PDF, not just the expected value. Now, when it comes to the variance, then we have, this is the expected value of n times the variance of x plus the variance of n times the expected value of x squared. And you can give a little bit of an intuitive interpretation to that result, and of course the variance of the total sum. And if your n was just a fixed number, then it's very clear that the variance of w has to be n times the variance of x. Now that we have the n as a random variable as well, it makes sense that we have one term that's proportional to the expectation of n times the variance of x. But then we have also something that accounts for the fact that the n itself is a random variable. That, of course, increases the overall variance. So the variance of n has to enter in here, and then it's proportional to the expectation of x squared to sort of keep the dimensions straight. And this is obviously not a mathematical derivation. This is just something to hold on to in the interpretation. But I would actually recommend to you that you derive the above equations from MGF rules, because we already have a law and a rule for how we get the whole moment generating function. Well, obviously, expectation and variance are just first and second central moment. So by using that law that we previously discussed, you should be able to just derive these rules for yourself. And as I said, it's a good practice for you. You know what the end result should be. It's completely up to you whether you want to go through with that or not. Okay, this finishes our discussion of two random variables, sum of random variables. We're now getting to topic of random vectors, which to a large degree is just a generalization of the things that we've done over the past 3-4 lectures. And we dealt with two, now we're dealing with n random variables that are related to each other in some form. And in order to keep the notation compact, we're going to write everything in a vector form. So you should probably be able by intuition to write down pretty much everything I'm going to tell you for the rest of this lecture already, but we'll step through the various equations and write them down in the proper notation. So let me just start out by writing notation. So we define a vector x, which is a column vector, and x1, x2, and so on to xn. We write x t as the transpose. Just for future reference, we're going to write x with that little cross on top as the Hermitian transpose. Now, for almost everything we're going to discuss here, we're going to stick to real random variables, but complex random variables, in particular complex Gaussian random variables, are actually very important in particular communications engineering. So, and a lot of the laws that I'm going to write down for real random variables that involve a transposition pretty much hold one-to-one if you replace the transposition with a Hermitian transposition. So I'm using the notation of a little arrow on top of a letter for a vector, particularly for a column vector, and I use an underline to describe a matrix. C1n. C1r, row n1, of course, sorry, Cn1. And then r is the number of rows. Sorry, something went wrong in my notes here. Let me. R is the number of rows, n is the number of columns, which of course means that this has to be C1n and this has to be CR1. Yeah, about that. So the only, you'll find in the textbooks usually just the X and the C as bold letters, but since with handwriting I can't really do bold, I'm using the arrow and underlining. We also define the norm of the vector as X transpose X, which equals the trace of X transpose, and we define the trace of C as the sum over all K of CKK for a square matrix. We define the inner product as between vectors x and y as y transpose x, and the outer product as yx transpose. Okay, that's just matrix notation. You've heard it in your undergraduate courses. You will hear it in E510, which you probably are doing in parallel in this semester, most of you. They might be using slightly different notation here, so that's why I'm just establishing the exact way in which we are writing things. But of course, it's the same equations, the same meaning. So now let's get to actual random vectors. So the random vector with a capital X is x1 to xn, where each xi is a random variable, and the vector small x is a vector of realizations. So here you see why we can't use the usual convention of saying, well, column vectors are small letters and matrices are capital letters, because we need capital column vectors as well to indicate the difference between what is a random vector, what is a vector of realizations. Then we define the vectorized cumulative distribution function. And so this is a capital X of a small x, which is f x1, x2 to xn of x1, x2 to xn. This is the CDF of a random vector. And we can similarly define a PDF of a random vector. And we can define a joint PDF of two random vectors, fx and fy, which is now simply x1, x2 to xn, y1 to ym. So basically just stacking the two vectors on top of each other, and we're saying, well, this is a distribution like this. So we could just concatenate x and y into one big vector w. It would be exactly the same thing. It's not necessary that the two vectors have the same length. And you see here I wrote them with the length n and the length m. They can be different. It doesn't really change anything in the description. Yes? They are functions, yes. We can have vector-valued functions of the random vectors as well, but that is in unusual situations. So the CDFs themselves are just functions that depend on many random variables. So to actually give a concrete example, we have an fx of x, which is 6 times e to the power of minus a transpose x for x larger equals 0, where we use here the notation that this is component-wise larger equals 0 and 0 otherwise. And the vector a is defined as 1, 2, 3. And so this is again just nomenclature for 6 times e to the power of minus, well, anyway, this is exponent of minus x1 plus 2x2 plus 3x3 for all xi larger equals 0 and 0 otherwise. And the associated probability density function would be now 1 minus e to the power of minus x1 times 1 minus e to the power of 2x2 times 1 minus e to the power of minus 3x3, again for the xi larger equals 0 and 0 otherwise. So you see this cumulative distribution function has the usual behavior that as x1, x2, and x3 all go to infinity, then of course the value of the CDF has to go to 1. If they are all minus infinity, or in this case, if they are all 0, because, well, we have no value, or we have 0 for the case for the xi negative, but if they're all 0, then the CDF is 0. So all the laws that we know for the behavior of CDFs are fulfilled in this particular case as well. And if we just reduce this to two components, well, you would see that this is exactly what we did 2 weeks ago. So it's really just a generalization. And yeah, as I said, it's mostly about nomenclature that you have to get familiar with. There's very little sort of special insights that are to be gained just from this generalization. Similarly, when we're dealing with independent random vectors, then the joint PDF of xy factors into the PDF of x multiplied with the PDF of y. Then we can define a vector of expected values which is again just component-wise the expectation of the individual random variables. Is just the way we always wrote it as the particular mu. And the same, by the way, holds for if we for some reason have matrices of random vectors as well. And now a little bit more interesting is that the expectation of the following product. So this is a linear transformation of my vector x. I pre and post multiply with matrices A and B, which are constant matrices, right, not random variables, and I add a matrix G. And so this can be then expressed because of linearity as A times expectation of x B plus G. And similarly, this holds, as I said, for matrices X as well. And where are we needing this for matrices? Well, when we're talking about correlations, because now we have the products of the outer products of the vectors to deal with. So the correlation matrix of a random vector X is the expectation of X times X transpose. And we know that by definition, or from the definition of the correlation matrix, R transpose equals R. Now that is a very important property, and that is maybe not completely trivial. I'm also telling you on a side note that for complex random vectors, the rule is that R Hermitian R Hermitian equals R. Now that may sound very trivial, but it actually turns out in practice it is not. In particular, let's say you have some sort of model, some sort of observation, and you want to create a correlation matrix. You might end up in a situation where your model, or what you use in terms of approximation of your correlation matrix, doesn't fulfill these symmetry conditions. Well, if it doesn't, then you know this is actually not a proper correlation matrix. And you will get into all sorts of trouble if you treat it as a correlation matrix. And just again, to hammer home that this is not a trivial point, is there was a paper not that long ago, maybe 10 years, 15 years ago or something like that, about the modeling of shadowing effects in wireless communications, where the authors reviewed a whole bunch of models, and about half of them were using assumptions for the correlation, quote unquote, that were actually not proper correlation matrices, and that didn't fulfill these conditions. And then you get all sorts of unphysical effects when you use them as the basis for your simulations, for your system analysis. And so this is really a pitfall that you have to watch out for as you're doing your analysis. So when we're looking at the individual elements of a correlation matrix, then you see that the ijth element of this correlation matrix, this is just how we write it again, and this is the expectation of the xi, xj. And for the covariance, we have that our Cx is the expectation of x minus mu x times x minus mu x transpose. And again, we have C transpose has to be equal to C. And for xi, xj, independent for all I unequal j, then C is a diagonal matrix. And so the cross covariance of all elements with I unequal j, all off diagonal elements, is just 0. And keep in mind that every covariance is positive semi-definite, which means that A transpose times C times A has to be larger or equal 0 for all vectors A. Now, this is another one of those pitfalls that you have to watch out for, and that was actually also a big part of that of this one paper that I mentioned. But again, as a general rule, if you establish a covariance matrix from measurements, and you have a finite number of measurements, so you actually only get an estimate, not the true covariance matrix, then you might end up with something that is not positive semi-definite. And again, this can create all sorts of havoc afterwards. In particular, if you, for example, know that for physical reasons, all realizations of the random variable have to be positive, but you create them via a not positive semi-definite matrix, then yeah, it could happen that you actually create realizations where the random variable is negative, and well, that's a non-physical situation that can cause your whole system or your whole simulation to completely break down or give you nonsensical values, right? So be very careful that if you derive a covariance matrix from measurements, like test for positive definiteness, right? So under any circumstances, right, test whether this is actually positive semi-definite. So we, of course, can relate the covariance matrix to the correlation matrix. That is just Rx. The covariance matrix is the correlation matrix minus the outer product of the expectation value. We also know that the value of the correlation matrix of the ijth entry is upper bounded by the square root of the ith element and the jjth element. And how do we know that? And how can we prove that? Well, this is by means of Cauchy-Schwarz for random variables. Who does not know the Cauchy-Schwarz law, the Cauchy-Schwarz inequality? Okay. Yeah, that is linear algebra bread and butter, obviously. And then diversion for random variables basically is just containing the expectations in the expressions. And then finally, we're going to deal with vector cross correlations. We let X run from 1 to n, so being an n times r matrix, and X running from 1 to n, and Y running from 1 to r, and so we're getting an n times r matrix for our cross correlation matrix, which is the expectation of X times Y transpose. Covariance, cross covariance matrix is again just the same thing, but with the expectation value subtracted. By the way, all of these equations that are here for the random vectors, they're going to be on the cheat sheet. I see no point in you memorizing those versions. It's also not exactly likely that you're going to get a vector exercise for the exam, because it's just a lot of extra writing without giving a lot of additional insight. So you're probably going to be limited to 1 or 2 random variables, just as a heads up. So if we now have Y being a linear transformation of a random vector X, and so Y being AX plus B, then we first of all find that the correlation matrix of Y itself is A Rx A transpose plus A Yx times B transpose plus B A Yx transpose plus B B transpose. The mean vector of Y is just A times mu X plus B. That's pretty straightforward. And the covariance matrix CY is A Cx A transpose, and the cross covariance matrix between X and Y is the covariance matrix of X times A transpose, and cross correlation matrix is the correlation matrix of X multiplied with A transpose plus Y, mu X, the expectation vector, times B transpose. Okay, that finishes at least some of the correlation aspects. As I said, it's all a little bit boring because it's just more or less a lot of notation. But we're going to now take a break. It's 9:01. We resume at 9:06, and then we're going to get to a little bit more interesting and new aspects of random vectors. Okay, it's 9:06. Let's resume. So you might wonder, well, if this is also boring and it's not showing up on the test anyway, why are we even dealing with it? Well, the reason is because that's what you normally are facing in practice. Right? I mean, the examples that we're going through with single random variables are all nice and good for explaining the concepts, but when you're dealing, for example, with a machine learning problem, then you have a very large dimensional vector of inputs normally, and each of which is a random variable. So all the processing that you're doing afterwards, let's say you have a linear first stage, a linear last layer, and so on, this is exactly, okay, you have a random variable multiplied with some sort of transformation matrix. And so exactly the equations that we wrote down. If you're dealing with a MIMO communication system, which is what you normally have nowadays with 5G and so on, then, well, you have the vector of signals at the different antenna elements, and again, this is a higher dimensional vector. You need to look at the correlation covariance matrix and so on between all elements, not just between a single one. And ultimately, this is also a little bit of a preview of what we're later going to get when we're dealing with random processes, because you can look at the values of the random variable at different time steps, and then you can also write those into a vector. So when we're later on going to deal with the temporal autocorrelation function of that is handled in a random process, then that is really just the same thing as what we were under certain circumstances, of course, of what we're dealing with here, of saying, well, what is the covariance vector of a vector X? And so it has its reasons and its motivations of why we are dealing with all this notation. And when you're ultimately then going into MATLAB to do your computations in the practical scenarios, again, MATLAB is based on, of course, all the vector matrix manipulations, and so you will be writing your equations in exactly this particular form. Okay, so let's now go to some additional definitions. And the first one is characteristic function, where we can now say that the characteristic function of a vector X is now depending on a vector nu, and which is basically the basis functions in the transform domain. And so our characteristic function is just defined as e to the power of j nu transpose x, which is nothing but an n-dimensional Fourier transformation of the probability density function. And that transition works if x has a joint density function. Remember that weird little example that I showed that we can't actually have multiple, just two random variables that do not possess a joint density function. So that can, of course, also happen when we're going into even higher dimensional cases. So that's why we always have to have that little caveat. And we can't really talk about these multidimensional characteristic functions if, in this formulation here, if that joint density function doesn't even exist. But if it does, and now if furthermore the xk are independent, then, of course, our characteristic function becomes the product of the individual contributions. And just as we had for the one-dimensional case, the nice thing about dealing with characteristic function as opposed to moment-generating function is that the back transform is simple because it's, again, just a Fourier transform. And we have here nu transpose x, phi x of nu du. So we've had already previously preempted a little bit the this rule when we're talking about the sum of independent random variables. But when we're dealing with actually multidimensional characteristic functions, we can see here that this whole thing more or less generalizes. Now, at this point, we're getting to something much more interesting, which is how do we actually generate higher dimensional correlated random variables, and what can we say about the impact of the correlation? So let's say that X has a covariance matrix C. Then there is a representation, and actually this representation is relatively easy to get because it's a linear transformation. So X can be written as P, a matrix P times Y, where the components of Y are uncorrelated. And furthermore, we know that P transpose P equal P transpose being the identity matrix. In other words, P is unitary. Right? So this is a really critical point. We're saying we have a whole bunch of correlated random variables, and if you look at the shape of a correlated PDF, right, so the Gaussian PDF that we were discussing, bivariate Gaussian variable, we said that, well, the isoclines, or the lines of constant of constant value were something that looked more or less like this in the xy plane. And then so if x and y are correlated, this was sort of the picture that we got. If we know x, then we know already something about the value of y. Now, what this Covenant-Leuven expansion, which is the name for this representation, tells us is that we can say that, well, we can always take this thing here, do a linear transformation into something where x and y are uncorrelated. And I pick x, I have no idea what's happening to y. So this is also the way of how we are generating multidimensional correlated random variables. And because we are going to first try and find that matrix P, then we're going to generate independent random variables, which is the easy thing to do, and then we're going to take that random vector with the independent entries, do the transformation on it, and that's going to give us the vector of correlated random variables. So this is both theoretically important and practically very relevant. And of course, from linear algebra, you already have an idea of how this could be done. Well, because we're saying our P transpose C times P has to be a diagonal matrix lambda with the entries lambda 1, lambda 2, and so on to lambda n. And you can say, well, this is just an eigenvalue decomposition. And so if we now say that, well, Y is P transpose X, as we postulate for a Covenant-Leuven expansion, then the covariance matrix of Y, according to the rules that we previously established of what happens to a covariance matrix when we multiply it with something, and is now P transpose C P, and that's exactly lambda. And so, which means that the components of Y are uncorrelated. And if C is singular, then we only need to keep the non-zero lambda. And the distribution of the eigenvalues of these random matrices in itself can also have very important practical consequences. And I mean, this is not going to be something that's on the test, but again, I just want to give you an example from sort of practical applications and more or less current research. You can communicate wirelessly over multi-antenna systems. Like you might have heard that catchword, MIMO communications. And there you basically say, well, I have multiple transmit antennas, I have multiple receive antennas, now there's multipath components going from transmitter to receiver, and so on. And so the signals that we have between each transmit and each receive antenna element is a random variable. Now, essentially, the signal-to-noise ratio, and therefore the capacity that you have for the transmission between these transmit and receive arrays, of course, is a random variable because of the fading that you're experiencing. And you might be thinking that, well, if I have n transmit, n receive antenna elements, then I can have n different data streams that I communicate, all of them have the same signal-to-noise ratio. Well, that actually works only if you have independent fading at all of the antenna elements. If you have correlation between the fading, which typically happens if your antenna elements are too close together, then you need to do a Carhart-Leuven expansion, or you basically need to look at the eigenvalues of those of the transfer function between transmit and receiver, and you will find that, okay, if you have strong correlation, then you have one eigenvalue that is very strong, the next one that is much weaker, the next one that is even weaker, and when you now look at what is the overall capacity, you're going to find that, well, it's really just dominated by the contribution from this one strong eigenvalue because everything else is so weak that you can't really use it anyway. And then that will give you results with much, much lower capacity than if you just assume everything is uncorrelated. So this eigenvalue decomposition or this Carhart-Leuven expansion that you have here is really critical in assessing what's the capacity of, let's say, a 5G wireless communication system. I'm actually just going to, for the fun of it, so that you see how things are translating between what is done in research papers versus what you see here, let me give you the formulation that you're normally encountering. And you basically say that you have a matrix H, which is the transfer function between the, so each entry corresponds to the transfer function between one transmit and one receive antenna element. And so these are Gaussian random variables. And your capacity of the system, I'm dropping certain constant factors now, is the logarithm of the determinant of an identity matrix plus a signal-to-noise ratio. Again, I'm dropping the constants of H times H transpose. And so the entries here are complex Gaussian variables. And this can now be written as, so let me write this as cap so that we don't confuse capacity and correlation matrix. And this can actually now be written as the sum over the eigenvalues of logarithm of 1 plus, and this here is now the eigenvalues lambda n times some constant. Lambda is the eigenvalues of H transpose. Now this equation is actually if the entries of your matrix are deterministic. If you're dealing with random entries of the matrix, you actually have here an expectation on the outside. And while it's very difficult to evaluate this thing in closed form, exactly, you can actually make use of what is called Jensen's inequality and say, I can pull this expectation here inside. Obviously, you cannot do, and this cannot be exact because the Ln is a nonlinear function. So you cannot just pull an expectation inside a nonlinear function and hope that everything is staying unchanged. But you do can say that, well, this is going to, what I'm going to get therefore here is going to be an upper bound. And so now this is basically going to give you the n expectation of the eigenvalues, which are actually randomly distributed. Sorry, I should write this as a lambda tilde, with the lambda tilde being the deterministic eigenvalues of the particular realization. And now you can say, well, this is actually corresponding now, this expectation of the lambda n is corresponding to the expectation of the eigenvalues of your correlation matrix, and that is going to give you now your capacity. That was the 3-minute explanation. As I said, don't worry, that's not going to be on the test. If you're interested in this topic, this needs a much longer description, and we actually deal with that quite a bit in 535, and multi-antenna systems, wireless communications is a strongly related topic. But as I said, it just gives you one example of why these Carhart-Leuven expansions and looking at the eigenvalues are so important. And when you now look at the question of, well, why is does this correlation play a role? Well, you have the logarithm of 1 plus expectation of something. So if your eigenvalues, for example, are 3, 3, 3, 3, if you have 4 eigenvalues, then you're getting the logarithm of 4 plus the logarithm of 4 plus the logarithm of 4 plus the logarithm of 4. And that's a nice number. If you have the eigenvalues, let's say, with the total same energy, but you're saying it's 11.5 and then 0, 1, 0.1, 0.1, then you actually get here the logarithm of 11.5, which is not that much larger than the logarithm of 4, and then 3 other terms that are basically nothing. And so that explains why this correlation is actually greatly reducing the capacity that you can have over your system. So don't think that, oh, it's correlated, but still the total energy is the same, so therefore we have the same system behavior. You really have to account in your analysis for the fact that, well, if you introduce correlation, things are changing significantly. Okay, now back to our regularly scheduled program. We are looking at functions of random vectors. We define a random variable w, which is g of x. Then the probability density function is the probability of w being smaller or equal to w, is the integral of g of x smaller or equal to w, integrated over all components of the random vector. And the expected value of g of x is, again, integrating over all components, g of x, fx of x, dx1 to dxn. This is, again, pretty much a repetition of what we had before. Now, a little bit more interesting is the question of how do we actually transform a random vector when we have a vector-valued output. So this comes a little bit back to the question that you were asking, I think, about half an hour ago. What happens if we have g of x being, let's call this y equals g of x, a vector-valued function, which means that we have y1 being g1 of, that can now depend, of course, on all the x1 to xn, and gn of, depending on all the x1 to xn. Now, I'm consciously picking the dimension of the vector y to be equal to the dimension of the vector x, because for most of the interesting things we want to do, we would like to have g to be invertible. And so if g is invertible, then we are simply going to denote the inverse of g as h, such that x is now h of y. And we are furthermore assuming that h is continuous and with continuous partial derivatives. Such that our dh of y can now be written as dh1 to dy1 to dh1 to dyn and dhn to dy1 to dhn to dyn. And so basically just every column is the derivative of the different components of h with respect to one of the variables, y1. Then the probability density function of y is given as the probability density function of x evaluated at h of y times the determinant, absolute value of the determinant of dh of y, where this expression here is known as the Jacobian. And again, you will recognize this equation, and when we're dealing with the one-dimensional case, we simply had here the derivative of h with respect to y, so this is just the multidimensional generalization of that fairly straightforward expression that we had before. So to give you a famous example of how we apply this, let x and y be independent univariate Gaussian, and we now are making the transformation from xy to r theta, which basically means we're going from Cartesian to polar coordinates. And we want to find out the joint density of r theta. So we can say that in this coordinate transformation, and of course r is the square root of x squared plus y squared, and theta is the angle of x and y, which is an ugly expression. Fortunately, we're not going to need it, because we're just looking at the reverse transformation at our h, and we're saying x is r times cosine theta, and y is r sine theta. So therefore, we can say, well, the transformation r theta is our g of xy, and conversely, xy is h of r theta. Now, we've written here the explicit expressions, so we can very easily compute now what is our Jacobi. Right? It's dx to dr, dy to dr, dx to d theta, and dy to dr. Sorry, dy to d theta, of course. And that is cosine theta, sine theta, minus r sine theta, and r cosine theta. You evaluate the determinant here, and that is r. So if we now plug this in, we find that f of r theta equals fxy evaluated at h of y, and h of y is r cosine theta, r sine theta, then multiplied with the Jacobian, which is just r, and so let's multiply this here. So now we plug in what is our fxy. Well, it's the bivariate Gaussian with independent entries, so that is just 1 over 2 pi e to the power of minus x squared plus y squared divided by 2, and multiplied with r, which is r times e to the power of minus r squared over 2, multiplied with 1 over 2 pi for r larger equals 0, and theta between minus pi and pi. Now, the reason why I was writing this in this particular form is that you can say see that this is actually our fr of r multiplied with an f theta of theta. So that demonstrates that even after this transformation, the two components, the r and the theta, are still independent of each other, just like the x and y were independent of each other. And that, by the way, is not a given. And in the general scheme of things, you're not going to experience that. Right? You start out with two independent variables, you take some vector value transformation of that, you're probably going to end up with correlated or not independent random variables. In this particular case, you are getting two independent random variables. And this is a result that's actually very important. So if you have bivariate Gaussian variables, could be, for example, because these are complex variables and you're looking at the distribution of their amplitudes and phases, you find that your amplitudes are distributed according to what is known as a radial distribution, and the phases are just uniformly distributed between 0 and 2 pi. And, for example, the radial distribution is what underlies the sort of worst-case fading in wireless communications. And if you open any basic textbook on wireless communications, that's probably one of the first equations that you're going to encounter. But obviously, the applications are much larger because Gaussians are occurring everywhere. And then, so two-dimensional Gaussians are a typical case that you're going to encounter. By the way, I previously said that, well, probably vector-valued things are not going to show up on any exams, but these, let's say, two-dimensional transformation of variables, right? Two-dimensional x into a two-dimensional y, what is the corresponding joint probability density function? That might be an exception. So let's come to the topic of multivariate Gaussians. We already saw last time for the bivariate Gaussians that things can start to look a little bit ugly. But so first of all, we're saying a vector x is Gaussian if any linear combination of its components is Gaussian. So we're saying that if C transpose x is normal distributed or Gaussian distributed for any C, any vector C, then this is Gaussian. And the joint probability density function of a Gaussian vector is given as the following expression. It's, first of all, 1 over 2 pi to the power of n over 2. So it's the 1 over square root of 2 pi that we have in the regular Gaussian to the power of the dimensions that we're encountering. And then instead of the sigma, we now have the determinant of the covariance matrix to the power of 1/2. And so again, obviously, in the one-dimensional case, that reduces back to the sigma. And in the numerator, we have e to the power of minus 1/2. Then we have x minus mu x transpose c x to the power of minus 1 x minus mu x. So again, if you're comparing this to the univariate case, we normally would have had here x minus mu squared divided by sigma. Now, since we have vectors here, we can easily write just something that is square, so this becomes x minus mu transpose times x minus mu. And instead of, again, a division by sigma, we have the multiplication with the inverse correlation matrix. And if it's, covariance matrix. If it's a one-dimensional covariance matrix, then this reduces to x minus mu times x minus mu divided by sigma, which is exactly what we have under normal circumstances, I mean, for the one-dimensional case. And x has independent components if and only if Cx is diagonal, which means that for Gaussians, uncorrelated is the same thing as independent. And I want to stress two things about it. Right? This is really important. Uncorrelated equals independent for Gaussians, and this only holds for Gaussians. And you can have uncorrelated variables with other distributions that still are not independent, where this decomposition of the joint PDF into the individual components doesn't work. But for the Gaussian, if it's uncorrelated, it's independent as well. Now, the characteristic function is phi x of nu is e to the power of j mu transpose mu x minus mu transpose c mu over 2. And again, that's just a generalization. Conditional expectation is now a normal distribution with a mean of x conditioned on a particular vector value y and a covariance matrix associated with it, and that mean is given as 8 times y minus mu y plus mu x, and the correlation matrix is cx minus a times cyx, and that mysterious matrix A is the solution to the following equation, a cy being cxy. And last equation for today, if Cx conditioned on y is invertible, then f of x conditioned on y is given as the following equation, which was not going to come as a surprise. Okay, with that, we are finished for today, and we finished the random vectors. Now, just as an announcement for next time, we are going to go there much deeper into theory. We're going to start out with some probability bounds, and then we're going to discuss different types of convergence and the central limit theorem. So this is going to be conceptually probably one of the most challenging classes, just to give you the heads up.